linear combinations are the most fundamental operation in all of linear algebra, because as we will come to appreciate when we look at the theory of vector spaces in V1 and V4 and so forth, linear combinations are the operation that is what makes vector spaces vector spaces. The ability to add vectors and the ability to multiply them by scalars are what make vectors vectors in the first place. And so linear combination, which is the combination of those two things, addition and scalar multiplication, is the sort of the foundation, the operational foundation on which linear algebra is built. And so in the first few activities, what you did was characterize, if you give me a collection of vectors, can you tell me what does the set of all possible linear combinations of those vectors look like? That set is called the span of that set of vectors. So, for example, if you give me these two vectors that are over here, 1, -1, 2, and 1, 2, 1, and ask what is the span of that set, it's the set of all vectors that we can create by multiplying one of those vectors by a constant and the other vector by a constant and then adding the results together for all choices that are possible for those constants. And so your job in these activities was to think about what does the span, for example, of the single vector 1, 2 look like. And as part of the assignment, you figured out, and I gave you a nifty little Desmos tool to kind of help out with it, you found that the span of this single vector 1, 2 just looks like the set of scalar multiples of the vector 1, 2. We don't have two vectors as part of our span, so we can only multiply this one vector by a scalar, and there's nothing else to add it to, really. So that by the time we look at all possible scalar multiples of this vector, what emerges is that the span looks like this line. It looks like the line y equals 2x inside of the xy plane. It's all of the points that we can get to by multiplying the vector 1, 2 by an arbitrarily chosen scalar. And generally, this is the picture that we will have anytime we have a non-zero vector and there's only one of them that we take the span of. Right? If you give me any non-zero vector in a vector space, the span of the set that consists of just that one vector is just going to be the set of all scalar multiples of that one vector. So everything which is parallel to it and everything which is anti-parallel to it. And so it's going to form what we'll think of as a line in whatever dimensional space our vector happens to reside in. And in the next activity, we up the ante just a little bit by getting two vectors in the plane instead of one. So 1, 2, and -1, 1. And ask, what does the span of those two vectors look like? And so for those, we get to pick a scalar multiple for the 1, 2, and also a scalar multiple for -1, 1. So we can pick any multiple of 1, 2, and any multiple of -1, 1, and add those results together. And if I do that, then depending on what multiple I choose for my 2, 2 vector and what multiple I choose for my -1, 1 vector, my results are going to be the blue points that are shown here. And as your groups correctly identify, it seems like we can get anywhere that we want to get to in the xy plane by taking some scalar multiple of one of these vectors and adding it to some scalar multiple of the other. So there really is no limitation on where we can go. So the span appears like it will give us the entirety of the xy plane. So we would say that the span is equal to R2, the entire of the xy plane. But the game changes a little bit if we pick the vectors 6, -4, and -3, 2 as the vectors that we want to include in our linear combination. So if I take one of these vectors and make it into -3, 2, and the other vector and make it into 6, -4, so I'll zoom out a little bit here, 6, -4. And then I take scalar multiples of one and add them to scalar multiples of the other and look at where the blue point winds up. It looks like, once again, we're in a situation where even though we have two vectors in my set that we're taking the span of, those two vectors are not enough to get us anywhere that we want to in the xy plane. It can only get us to points that lie along, apparently, this line. So what was it about these two vectors, -3, 2 and 6, -4, that make it so that we can't explore all of the xy plane through linear combinations of those two vectors? What would you say? So this is a pathological example because one of the vectors in my set is already a scalar multiple of the other, right? So there is already a interrelationship, a linear combination interrelationship between the vectors that are a part of my set. So even though I have two of them, they are not, I'm going to drop an important word here, independent of one another. right? One of them is a scalar multiple of the other, and so neither of them can get you somewhere that the other one can't already get you, is another way to think about it in terms of linear combinations. So there's no way that the linear combinations of both of these vectors can include something that the linear combinations of just one of them already don't include, right? So there's a dependence, an interdependence of these two vectors on one another that we're going to make more precise when we get into section V5 next week on linear independence. So with this groundwork laid, now that we know what linear combinations are and how to think about what the span of a set of vectors looks like, the set of all of its linear combinations, the sort of big culminating activity in this section was this one, where we're told that the vector -1, -6, 1 belongs to the span of these two vectors, 1, 0, -3, and -1, -3, 2. And that's true exactly when there exists some linear combination of these two vectors that adds up to give me this one. But that statement, that there exists a linear combination of these two vectors that adds up to the third vector, is really a vector equation which we can reinterpret as a system of linear equations in the unknown coefficients of my linear combination, which we're calling x1 and x2 here. So x1 of the first vector added to x2 of the second vector may or may not be able to equal this third vector on the right-hand side. If that system has a solution, any solution at all, no matter how many solutions, as long as it has at least one solution, then that means that this vector does belong to the span because it is some linear combination of these two vectors. On the other hand, if this system is inconsistent, if there's no solution, then this vector doesn't belong to the span. And so to investigate the question about whether or not this vector belongs to the span of these two, we just have to set up the associated vector equation and then use our techniques from the first chapter to figure out if that equation is consistent. And so let's take a quick look at what one of your groups wrote down for this part of the problem. So what group 2 wrote down is that this vector equation, whose solution, if it exists, tells us that -1, -6, 1 is a linear combination of 1, 0, -3 and -1, -3, 2. When you write it out in coordinates, looks like x1 minus x2 is equal to -1, 0x1 minus 3x2 is -6, and -3x1 plus 2x2 is equal to 1. So it's a system of 3 equations and 2 variables. And so we might be concerned that this is an overdetermined system. Anytime we have more equations than we have variables, it seems like we're trying to bind too few quantities with too many constraints. And so we start to worry that there might not be a solution in general. But we don't know for sure until we actually try to solve this system. And this team did that by putting the system into an augmented matrix form. So 1, -1, -1, 0, -3, -6, -3, 2, 1. So using the augmented matrix strategy from our first chapter, and then finding the reduced row echelon form of that augmented matrix. And finding out that this reduced row echelon form corresponds to a consistent system of equations. What is it about this RREF, by the way, that tells us that this system is consistent? The important row in this reduced row echelon form is that last row, the row that's all zeros. And so if I convert that row back into an equation, it tells me 0 is equal to 0, which is a true statement regardless of the value of x1 or x2. Right? And so we can ignore that that row of all zeros is there and focus on the other rows in our reduced row echelon form of our matrix. And those other rows tell me x1 is equal to 1, x2 is equal to 2. And therefore, if we take 1 times my first vector and add it to 2 times my second vector, we get the right-hand side, the -1, -6, 1 vector that we were hoping to get. So this is a consistent system. In particular, there's only one solution, and that one solution is x1 equals 1, x2 equals 2. But most importantly here, because it's consistent, it means that the vector -1, -6, 1 is an element of the span. It is a linear combination of the vectors 1, 0, -3 and -1, -3, 2. So that's the recap of the linear combinations work that we did last week. So what we want to do this week is push that to the next stage. And the next stage is going to be to think about what are called spanning sets. So as the name suggests, this is going to be something that's closely related to the ideas of linear combination, but it's almost sort of going backwards, where we have a vector space and we have a collection of vectors within that space. And the question is, are these vectors enough such that their linear combinations give us the entire space that we're looking for. So it's almost like going backwards. Instead of taking some vectors and asking what do they span, we're taking a vector space that already exists and says, are these vectors within it enough to span everything that we would need in that vector space?